Hello students, and welcome to this video about test number 4. Under test 4 you have 4 files: questions, solutions, the data file, and the research article. We're going to begin by looking at a previous research article from 2001 which introduced a method for non-parametric multivariate analysis of variance. And this paper is describing a method called PermaNova. And here's an important picture. This is a geometric representation of MANOVA, which is multivariate analysis of variance. And then here's another important picture. Okay, the sum of squared distances from individual points to their centroid is equal to the sum of squared interpoint distances divided by the number of points. So this is an important identity that is used and that we'll be using in this test. We will also be using the Bray-Curtis distance, or the Bray-Curtis dissimilarity measure. And we'll be using this type of statistic. We'll compute our p-values using permutations. Okay, so let's go into the other research article, which has the mathematics that we're going to be implementing. So this more recent article came out in 2017, and you see the same person, Marty Anderson, is also an author here. And they kind of review some historical facts about statistics. And they review PermaNova, where they introduce step by step these symbols and terms and mathematical objects that lead up to this F statistic. Now here, everything is identified in terms of matrices. So you have the trace of a matrix product in the numerator, and in the denominator you also have a trace of a matrix product. Now, a lot of the matrices that you're reading about here come out in the basic linear algebra course, like the unit matrix Jn, or the identity matrix I, or the hat matrix H. And also the Gower matrix is going to be defined based on the dissimilarity matrix. So G will be the Gower matrix, H is the hat matrix, I is the identity matrix, and then I minus H is called the residuals projection matrix. Okay. And you can learn a lot more about H and I and J and other similar structures in the linear algebra course. Then they introduce this modified PermaNova, and they make a change in the denominator. So in the denominator now they have the sum over all the groups of the within group dispersion VI multiplied by this constant, or by these constants. And they point out in this part of the paper that this form of the F statistic, number one, it allows you to have a null hypothesis about equality of group centroids, allowing for possible differences in the group dispersions, and also allowing you to have different sample sizes. They also mention when you read this that when the sample sizes are the same, then it would be equivalent to this top statistic. Okay. So you could run through this, and they talk about the residuals vector, the residuals matrix, I mean. This is the projection matrix for residuals, I minus H, where I is the identity matrix and H is the hat matrix. And then there's a residualized G matrix, which would be R. And then they define UI to be a group indicator vector for group I. And then you can define a diagonal matrix capital UI with the diagonal, which is the little ui. And then you can get the residuals projection matrix for the ith group in this way. And then they point out that the within group dispersion can be calculated as the trace of the within group or with the group residual projection matrix H times G, and then you get the trace, and then you divide by the group size minus 1. So what we're going to be doing in this test is working with a categorical data set. So we're not going to have any numbers. We're just going to have categorical data. Either you have a species present or you don't have a species present. So when we open up the data file, what we see is that there's one variable that's a control variable and telling you whether you're in a control group or not. Then we have these 4 species of bacteria, and their presence in the sample is 1, and if 0 is there, the species was not detected. And so what we would like to do is understand, is there a difference in these 2 groups, the yes and no group, in the bacterial composition? And one way we can try to measure that is with the centroid. Do they have the same group centroid? So here you have zeros and ones. So these could be categorical variables. You don't have to code them as zeros and ones. You could put them as like present or not present. So when you're thinking about this test, you're thinking that you're only working with categorical variables here, absence or presence of individual species. Okay. So let's go to the solution file and look at what's involved in trying to carry out this calculation. So first of all, you can read about the Bray-Curtis dissimilarity for presence-absent data, and it's defined as follows. The distance between I and K would be A plus B minus 2J over A plus B, where A is the number of species in site I, B is the number of species in site K, and J is the number of species that were found at both sites. And so this is a dissimilarity matrix. Note that if you have I with itself, the same site, you would get 0. It's also reflexive. But it's not a distance. This is actually not a distance measure. Okay. And then, as we roll through these bullet points, these are matching up with what was being defined in the research article from 2017. Capital Y in boldface is the N by P matrix of multivariate row vectors. So in our case, P will be, P here will be 4 because we have 4 species. G is the number of groups. Ni is the size of the ith group. N is the total number of observations, which is the sum of this Ni's. And then D is the symmetric matrix of distances or dissimilarities. And here we're using the Bray-Curtis dissimilarity for binary data, which is for presence, absence, presence data. I sub n will be the n by n identity matrix. J sub n will be the n by n unit matrix, which is the matrix that just has ones everywhere. Hn is the centering matrix, which is In minus Jn over n. A is defined as negative 1/2 of the Hadamard product of D with itself, which is just element-wise multiplication. So the elements look like this, minus 1/2 of D ij squared. Then you should be aware that there are 4 matrices or 3 matrices that you can get from A. There's the matrix of row means, there's the matrix of column means, and there's the matrix of the overall mean. And then the Gower matrix is defined in terms of A, and it looks like this. Its elements can be thought of like this, but it's also equal to Hn times A times Hn. So if we want to get Gower's matrix, then what you have to do is get the distance matrix. Then you get this A matrix, and then you multiply by the centering matrix on either side, and you get Gower's matrix, and you can understand it to be this, having elements that look like this here on the left. Now the hat matrix, which we're going to call H without an N, is defined like this. And these equations match up with what you get in linear regression. So this comes from the normal equations in linear regression, and it can be derived with a multivariate calculus. So if you take linear algebra, you may learn that. Remember, the prime is the transpose, and the -1 here is the inverse. Okay. And then VI, or VL here, is the within group dispersion, It ends up having this definition in the research article, and then you could define F2 like this. But if we switch to matrix notation, we can also get the denominator in a different way. So this is the residuals projection matrix, which is I minus H. Then this is the residualized G matrix. UI is the group I indicator vector, which is of length n. UI is then the diagonal matrix whose diagonal is small ui. And then the group I projection residuals matrix is H, I like this. And then H, the projection matrix for residuals overall is just the sum of the individual group residual matrices. And then you can get VI, which was a group I within group dispersion, to be the trace of HI times G. And then you divide by Ni minus 1. So in our computations that we're going to do, we are going to use this bottom way to compute the test statistic. We're just going to try to work with matrices. So here we've imported the data set. So we can use the read CSV function. And then I want to rename control group to be called group. So there's a function called rename that allows you to rename the columns or the variables of your data sets. But keep in mind, this is a double pipe operator, which takes something from the left, passes it to the right, carries out a computation, and then reassigns back to the left. Then we're going to go ahead and create Gowers matrix G and the hat matrix H. So we need n, which is the number of observations. So I can use n row. And then G will be the number of distinct groups. So G is assigned to be data set piped to pull out group, piped to unique, piped to length. That gives me 2. And then I can use to get the values of N1 and N2, I can do this. So M is assigned to be a data set piped to group by group, piped to summarize, and then I can assign these values of N. Now, there's a typo here. You shouldn't have N3 or N4. Okay, so I'm going to go ahead and delete that. So when you look at the PDF, if you download the PDF, you shouldn't see N3 and N4 here. We only have 2 groups, so there's only going to be N1 and N2. Then we need the sum vector, which is the vector of length n that has 1s everywhere. And one reason they might call it the sum vector is that if you do the inner product with another vector of length n, it just results in the sum of the other vector. So Jn is the unit matrix, and it's the outer product of the sum vector with itself. And so that's the n by n matrix that has 1s everywhere. And then In is the diagonal matrix whose diagonal is all 1s. And then the centering matrix is the identity matrix In minus the unit matrix divided by n. Now to get the data matrix, we say Y is the data set, passed into select, I take away the categorical variable group, and then I turn that into a matrix. So then Y will be my data matrix. We need P later on. So P will be the number of columns of Y, that's the number of variables. And then to get the distance function using the Bray-Curtis dissimilarity, you could do it manually. Like you could use the outer function, and you could work to develop the function from, or the distance matrix from more basic principles. But in the vegan package, there's a VEG distance function that allows you to specify that the method is Bray, which will be Bray-Curtis dissimilarity. And if you want presence-absent data, which is just 0, 1, then you have to specify binary as true. So this is how we can get D to be the distances, not the distances, but the Bray-Curtis dissimilarity for presence-absence data. Right? Then I'm going to turn it into a matrix because this will be a VEG distance object, right? And I want to use it as a matrix. So then I have to, after I define D, I got to turn it back into a matrix. Then we get A like this. Remember that the asterisk here, if I do a matrix times a matrix just using the asterisk, that's element-wise multiplication, also called the Hadamard product. Then we have Gowers matrix G, which is the centering matrix times A times the centering matrix. And then we need X to be the group indicator matrix. So X will be data set passed to mutate, and I have a column X1 and X2, and these are just group indicators. So I have as dot numeric, group equal unique group 1. So the double equal is a relational operator, so it will test whether you have equality or not and return true or false otherwise. And then as not numeric will turn true into 1 and false into 0. And then I can pipe that into the select function, and I just want to keep these two columns x1 and x2 that I had just defined. Then after that I turn it into a matrix. So this is how I can create the group indicator matrix, capital X. Then I can assign column names, and then I can define the hat matrix using the solve function and the T function, which is for the transpose of a matrix. Remember that if you want the inverse of a matrix, you can use solve. Something to be aware of is that X will be a rank 2 matrix. It only has 2 columns, and they're independent of each other, so it will have rank 2. So the transpose of X times X will be a 2 by 2 matrix of rank 2. Because remember that the rank of the transpose of a matrix times itself is equal to the rank of the matrix, which is 2. And if you have a square matrix whose rank equals the number of rows, then it's invertible. So this will be an invertible matrix. All right, there's our hat matrix. Then we continue on with what the research article says. We want to get the group indicator vectors, would just be the columns of the group indicator matrix. Remember, you can access the columns of a matrix by doing the name of the matrix and then the column and the number of the column you want. So these are my group indicator vectors. And I can use those together with a diagonal function to get a diagonal matrix whose diagonal is this diagonal, or is this U1 vector or this U2 vector. Then we can get the group residuals projection matrices using the identity matrix and the hat matrix and these capital U matrices. Then from that, we can compute the within group dispersions using the trace function. So this TR function is actually from the psych package. Okay. So remember, the trace of a matrix is the sum of the diagonal elements of the matrix. So those are my within group dispersions. And the next thing is to go ahead and calculate the test statistic. So the denominator has this form. The numerator has this form. And then F2 would be numerator over denominator, and it ends up being 5.25. So that is our test statistic. Now, if you read the book carefully, or if you read the research article carefully, they will tell you that under the true null hypothesis, if the null hypothesis were true, then the expected value of this F statistic is 1. Okay, or maybe they don't say that, but they say that the expected value of the numerator and denominator are equal to each other. And so the F2 would be close to 1. And we're getting something bigger than 1. Now to compute the p-value based on the test statistic, we need to define a function that will permute the rows of the group indicator matrix and then recalculate F2. And that's what we see. So F is a function of X. And the first thing to do is take the matrix X, which was our group indicator matrix. And for the rows, we sample. So I'm going to sample 1 to n of size n without replacement. So that will be a random permutation of the rows of X. So that's equivalent to randomly permuting the groups. Then you have to recompute the hat matrix, the group indicator vectors, the diagonal matrices, the group residual projection matrices. You have to recompute the within group dispersions. Then you have to recompute the denominator and numerator, and then you can get your F2 statistic. Then you want to do that like 1,000 times or 5,000 times or 10,000 times. Here I just did 1,000 times. And I see the p-value came out pretty low, 0.01. So that would usually be considered statistically significant. Right? And the next step is to draw a histogram of all those 1,000 values. So here we need to build a tibble. So I say Q is a tibble based or containing X null. So when I just supply X null in there, that's also going to be the name of the column. And then I have G hist is ggplot connected to the data Q, plus a geom histogram mapping AES. X will be X null, and y will be dot dot density. So the dot dot, remember, is a computed aesthetic. This dot dot density is not a part of the tibble of the data argument. Okay. Now breaks, I wanted it to go from 0 up to the max of qx null, and I want there to be 40 bins. Okay. And then I add a geom v line where the x-intercept is the test statistic that we calculated. And I can use scale x continuous to control the x limits of the plot. And I can use geom text to add text. I can use labs for the labels, and I can use theme to control other aspects of the plot. But this is what the permutations look like together with the computed test statistic that we did. Okay. So we wanted to test whether the bacterial composition is different in these two categories of people. And to do that, we use the Bray-Curtis dissimilarity for presence-absence binary data. And then we went ahead and used the modified permutational multivariate analysis of variance that was presented in that research article, and this is what we have. And so you can interpret this as that what we're observing is very unlikely under the assumption that the null hypothesis is true. And we would therefore say, well, we can reject the hypothesis that the null hypothesis, or that the bacterial composition in the two groups is the same. Now that would further be supported by some scientific evidence, right? Like you don't just report a p-value, you also would like to know that there's some logic or some reason to believe that there's a difference. All right, another important visualization here would be the PCOA plot, principal coordinates analysis plot, which is based on the eigenanalysis of the Gower matrix. So here Q will be eigenanalysis of the Gower matrix, and then you take the vector. So the columns of this eigen-G vectors, those are the eigenvectors of the Gower matrix. And when we do a PCOA plot, we just get the first two. So those correspond to the two biggest eigenvalues, so that they represent the biggest proportions of variance. Then we can assign column names. Then we can turn Q into a tibble. And then we can pipe it to mutate and add group to be the dataset group. So now I have the group data in there. And then I'm going to create the PCOA plot, the principal coordinate analysis plot. So it'll be ggplot connected to the data Q. And I'm going to use geom jitter. So geom jitter is like geom point, but it adds a little bit of random shaking so that when you have overplotted points, you can see them instead of having them stacked up on top of each other. Mapping equals AS, X is axis 1, Y is axis 2. Color and shape are both group. Then we can add geom circles. These geom circles were added at the end, and I'll show you why. So the geom circle comes from the GG force package, and the GG force package has that function geom circle. It also has geom ellipse, which can be helpful. And this is the PCOA plot, and you see that the pattern of the points is not random with respect to the categorical variable control. Like I have this group of points up here, they're all green. There's 1, 2, 3, 4, 5, there's 7 points up here. They're close together. They're actually probably at the same spot because there's only 2 to the 4th or 16 possible locations for points on this, but with geom jitter it's spread out. And then I have another group down here, and these are almost all the orange circles. And there's a couple green ones, but what you see here, this is not a random pattern, right? There's something going on with regards to the categorical variable group indicator, right? So there's statistical significance, and we see another way to see that is in this pattern. And we can combine them using the patchwork package. I can combine them together into a plot and save that plot. Okay. All right. That was it for your test, but it presents you with the opportunity to learn all kinds of new stuff. One, you can learn about doing a principal coordinates analysis plot, which is based on the eigenanalysis of the Gower matrix. And you can also practice building up the Gower matrix using elementary matrix operations. You're also doing a multivariate analysis that is based on a dissimilarity measure. That's a new thing. And you can read through that research article and learn a lot, okay? One thing I hope that shines through from this example is the importance of the matrix algebra. If you can get good at matrix algebra and learn how it applies into statistics and multivariate analysis, that's a pretty cool application of mathematics. And it can lead you into lots of other things. So you know PCOA, you know about permanova, you know about modified permanova. You know that you can apply that on dissimilarity matrices, and you can apply it for categorical data. All right, that's it for this video, everybody. Good luck, and I hope you all are able to learn from this, and I'll see you on the next video. Bye-bye.